Okay, Ramit, I think we can start.
Sure. All right. So today I'm going to discuss about this paper. The paper's title is Low Rank Adaptation of Large Language Models. So it's sort of an interesting, linear algebraic trick that they do in making fine-tuning large language models a lot easier. So the method is very actually like straightforward. So it might be very maybe a short presentation, but yeah. So just at a glance, this paper LoRa, it's a simple idea. And so the problem they are tackling is a faster way to fine-tune language models. So it doesn't necessarily apply to language models, but any dense layers in general. Yeah, so the way they do it is through training indirectly. We'll talk about this in detail. And through this method, there's no additional latency. So we'll quickly look at the motivation, background, and the related work and their results. So we know that like from maybe 2016 or so, language models, people are scaling language models with higher and higher parameter counts. So there are some like closed source language models like GPT-3. I think the weights are not available, and there are some open source very large language models as well. And even though these are very general purpose, like it encapsulates all the knowledge in the world to one model, usually for specific tasks, people fine tune these language models. Let's say for maybe a financial language model for the financial analytics or something like that, or maybe for medicine. Likewise, people fine tune for specific tasks. Even though they seem general to obtain better performance. So like the author mentions, if we take the GPT-3 few shot performance, that is, I think, the general model. So the performance increase when we fine tune on those particular tasks. However, the problem is if we want to fine tune a specific task, it becomes very compute intensive. So for example, let's say, so the authors of this paper are from Microsoft. So they, in the extreme case, they evaluate on the GPT-3 model since they have access to that. So, so the thing is, if we want to fine tune billions of parameters, it takes a lot of compute, and it's very hard to do that. So apparently it takes like, I think 97, 96 V100s, and the checkpoints of the models are like 1 TB of this model. So if we look at why this like problems occur, we know that if we want to fine tune a model, we basically unfreeze all the
So
parameters, billions of.
I have a
Yes.
question. If you go back to your previous slide, so
Yeah.
you said GPT-3 is like not open source, right? And the weight, we don't have the
Yeah.
weight. How do they find the
I think
authors
I
from?
think yeah, I think the authors are from Microsoft. So yeah, I was initially wondering that as well, but I think there's a technical report on GPT-3, but I think it's not open source.
Yeah, okay.
Yeah. So if you want to fine tune the model, let's see why we need a lot of compute and memory. So as we know, when we use uh, adaptive moments optimizers like Adam, we essentially need to calculate the gradients and the first moment and the second moment. So for each weight, we need to keep track of this exponential moving average of the gradient and the squared gradient. So that is why we have to keep all these things in memory, and natural because of the number of parameters, the floating point numbers that we want to store, we need a lot of memory. So so now the question is whether we need to fine tune all of these parameters or whether we can fine tune maybe a subset. So in general sense, this is not just applicable to NLP, but what we can probably think about is training some subset of parameters of the model, or we can just plug it in some external couple of layers or something to do the fine tuning. So through this, we can have small number of task specific parameters, and it's much more efficient to train something like that. But the thing is, we might encounter additional overhead from the external MLP layers or external attention layers that we introduce. And if we just select subset of parameters or introduce some parameters into the model, we might have some performance issues. So that's the, in essence, the problem of selecting a subset of parameters to fine tune. But in NLP, I think there are much more sophisticated methods than this that they compare with. For now, I'll just like keep it simple. Like in essence, if we approach in this way. So in their approach, they basically gain inspiration from a couple of papers in 2018 and 2021, I think. So the main thing that they mention is these overparameterized models reside on a low intrinsic dimension. So this intrinsic dimension, the word actually, like, it was coined by a paper in 2018. Yeah, so in summary, even though we train some overparameterized model, there could be some intrinsic dimension where we can actually have less number of parameters to just tackle that problem within the similar performance. So yeah, so this is like a citation that they mention. So this intrinsic dimension, like if we quickly look at what that means. So this is the paper, I think, initially which coined that term, intrinsic dimension of the problem. So, in summary, like what this paper mentions is, so the number of parameters that we need to train to tackle the problem might give us a rough idea how complex the problem is. So we keep increasing the number of parameters, and it might give us a sense how complex the problem is. But these authors ask the question whether is that really corresponding to the complexity of the problem. So yeah, so I think they I'm not exactly familiar with the experiment, I mean the methodology of this method, but in a sense we can think that they increase the dimension of the subspace such that they can tackle the problem. So they call this the intrinsic dimension. Yeah, so this is the term intrinsic dimension. So if we look at the yeah, so if there's another paper in from Facebook AI group, so they mentioned that this came after that previous paper. So so after we train a model with overparameterized number of parameters, they mentioned basically that there exists a low dimensional reparameterization that can be used for fine tuning. So I think in this paper, they selected a subset of parameters. So specifically, they mentioned here 200 randomly trainable parameters randomly projected back to the full space. It can still achieve 90% of the full performance. So this paper has more like observations that they do. For example, they mention if we pre-train a language model longer and longer, the intrinsic dimension lowers as well. So so basically, if we have a better pre-trained model, because of that, like gained particular knowledge, it's very easy to adapt very few parameters for a particular task. So I think it's worth to sort of look at these papers. I'll just briefly touch the abstract of it. So with these ideas in the past, this paper asked the question. So basically the previous paper said, we can select a subset of parameters and fine tune. So like as I mentioned previously, optimizing 200 randomly parameters could still achieve 90% of the full performance of this Robert model. So now this LoRa paper reframes fine-tuning like this. So we have the weights of the, let's say, 175 billion weights. What we essentially do after fine-tuning is gain some delta W weight matrix update that is essentially added to this weights. So after some fine-tuning steps, we are just calculating some offset of these weights. So so what they hypothesize is that this updates to the weights can also have a low intrinsic rank when we adapt to a new task. So that's the key question they ask. So if we look at this, so in a matrix, what we think about the rank is, so if there are particular columns that we can express as a linear combination of other columns, we can eliminate those columns, and essentially it lowers the rank of a matrix. So through rank decomposition, what we can do is, if we have this D by K dimensional matrix, let's say so this A should be actually W. So if R is the rank of this W matrix, we can decompose this into matrix multiplication B into A, where there's a dimension R, which is equal to the rank of this matrix. So rather than having a D by K matrix, we can just express in number of parameters. So what the authors of this paper do is, so if we look at it again, in essence, after fine tuning, we have W not, that is the in pre-trained weights, and this is the updated weights. We can express the the effect of these as the input into the W naught matrix and delta W matrix. But the thing is, this, since we hypothesize that these updates also lie in a low intrinsic dimension, we can express this the difference matrix through this rank decomposition. So it's just like that big matrix we are representing as a matrix multiplication B into A. So it takes less number of parameters. So in this paper, I think they even try the R dimension as 1 or 2 as well. It's so that there's maybe there's so much number of parameter reduction. So because of this reparameterization, they need to just keep track of those gradients, the first moment, second moments, only for small number of parameters. So there are a couple of details on this reframing about the initialization. So the A matrix is initialized from a normal distribution, and initially this B matrix is 0. And they mentioned about some scaling factors on how exactly they implement this. But in essence, if we train this way, we essentially freeze these W parameters, pre-trained weights, and we just, so it's a constant, and we just update these parameters and fine tune. The nice thing about this approach is, so once we do this fine tuning, for each tasks, we have just few parameters, A and B matrices, that's task specific. So rather than just storing, let's say,
Ramit, so H is the output?
Yeah, H is the output of this layer, we can think.
Okay, so H is the output of the layer, and then so it basically have one path from the pre-trained weights, and then there's another path through this low rank weights.
Yeah.
And the low rank weights is linear. So you add, or so I mean, this is a linear, this is the linear layer.
Yes, this is a linear layer actually.
Okay.
Yeah.
So for every layer, you need to have these two paths. It's like a residual for every layer.
Yeah, so I think in the transformer, there are particular language model, they do this for the query and yeah, yeah, those matrix multiplication, two of those matrix multiplication of the transformer block, they do this.
Okay.
Yeah,
Yeah.
they are yet to evaluate this on like MLPs and layers with biases, but in the context of the language model, they just do this for the yeah, query and value
Understood.
matrix transformations.
Yeah. Cool. Okay.
Yeah, so once they do this sort of residual path, so as we discussed, for a specific task, they have just AB matrices. So there are a couple of, I mean, this is just illustration of one dense layer. But the beauty of this is once we have this AB matrices, we can just like add those. So we saw that in this equation, like we can take out X and just update the pre-trained weights by summing up the B into A matrix. So during inference, there's no additional latency. We can just have some updated weights. So compared to other methods, this does not necessarily add in other external stuff to the network. And during the training, it's much more efficient. So yeah, so particularly to their transformer or the Roberta model, they actually apply LoRa to these two matrix transformations to reduce the number of trainable parameters. Yeah, so I think this is regarding the paper, the method of the approach, and this is sort of widely adopted in language model fine tuning, I think, as of now. So they demonstrate this approach on an open source model called Roberta. So this bitfit and adaptation, these are like other approaches, I suppose. And they say that even with a low number of parameters, trainable parameters with LoRa, it achieves very competitive performance. So yeah, so let me go to the GPT-3 results. So here, yeah, it has 175 billion parameters for the like pre-trained task, and so I think this is like yeah, the first one is fine-tuning all the parameters. However, with just with just 0.02% of the weights fine-tuned, they can achieve very better performance. So I think this is because that intrinsic dimension observation that authors did in the past. Like when we are fine-tuning for a new task, there's like a very low dimensional space that we can just manipulate to get better performance. Yeah, so there are slight performance like here, even though it has higher number of parameters compared to the 4.7 million case, there's like a bit of degradation here. So they mentioned that not all methods benefit monotonically when we increase the number of parameters. So here, this like the triangle represents the LoRa approach, and other approaches sort of fail when they increase the number of parameters. That's what they show here. So this, so these are the like two columns that we showed earlier, and showing it as a graph. So I also have a doubt here why this model has a little bit less performance than the like lower parameter model. Like I mean these two values. So probably it might be some optimization issue when the number of parameters get large, I suppose. Yeah, so I think it's, in essence, that's the approach. Yeah, so yeah, so in this study, there are a couple of things that they leave for future work. So layer norm and biases, so they leave it for future work, and currently they adapt this LoRa approach to query and value matrices. Yeah, so I guess that's all the slides I have. So these are some references I looked at it to understand the paper. Yeah.
Right, sounds great. It's actually very neat idea, I think.
Yeah. Mm.
So basically, in other words, like what you're saying is that some of the changes to the weights are correlated, so you can kind of like find the projection matrix, right?
Correlated in the sense like if we manipulate these small matrices, we can basically derive the effect that happens to other uh, linearly dependent columns, I guess.
So the dependent ones will be changed together, right?
Yeah.
So in general question I have is like, so these large language models, like they are trained for basically like language stuff, right?
Yeah.
But what I try to just put like images like into the language models and then see like what type of embeddings you get.
Yeah, the closest thing that comes to my mind is that I think mask coding paper that they do for imaging.
I mean, like, in other words,
Mhm.
are there like any foundation models for images, that one can just use?
Right,
Yeah,
right.
you mean multimodal LM? Uh, sorry, you mean kind of like multimodal LLMs?
Not really. I'm just yeah, multimodal is definitely one thing. But even without like language part, just like any model that is trained with images, for an example, just as like an image embedding
Mhm.
network type thing. I guess the motivation is to see whether we can have something that that we don't have to train a model from the scratch, but can we just like use some big model that has been trained on all the images in like, millions of images in the world, other than our like classical image technology.
There was one paper which I recently saw on pathology image analysis. Actually follow. Yeah. Visual language foundation. So they actually obtain pictures from public forums like Twitter.
Yeah, I saw this paper, I didn't read it yet. Right, all right. Any other questions?
Shihan, regarding the multimodal case, are there like so I remember Kitmini presenting about image bind. So
There's a paper called Lava. I think the model is Lava. Paper name is, I think, Visual Prompt Tuning or Visual Instruction Tuning. So that tries to uh, introduce a projection layer that maps the input image into the LLM's input space, which is textual representation. So then, it's kind of similar to GPT for that kind of multimodal LLM, and it's open source. So there are many work that's built on the top of Lava.
I see.
What's it trained on?
Mm,
specific
one
or
dataset was used to train lava.
Mhm.
I think, as I remember, they use their, I think they create their own dataset, lava 150K, or I don't remember the exact name. LLAVA. Yeah, I think that one.